So, very good evening to all of you, and for all those people who are joining from Pacific region, a very good morning to them. And I welcome you all for the 12th Professor P. Ramachandra Rao Memorial Lecture. And we are happy to say that Professor K. F. Kelton has kindly agreed to give this memorial lecture on crystal nucleation in liquids and glasses. This area was very close to the heart of Professor P. Ramachandra Rao. And before we begin, I will just ask you to ensure that the audio and video are muted, and you can adjust your settings for optimal viewing. And with this, I would request Dr. Sandeep Ghosh Chaudhary, Director, National Metallurgical Laboratory, to deliver his welcome address. Dr. Chaudhary, please.
I think good morning to our Indian friends and good morning to Professor Kelton and from the UK, Professor Hari Rao. Now, it's with great respect and the heartfelt gratitude that I welcome you all to this 12th Professor P. Ramachandra Rao Memorial Lecture. Today, we gather not only to honor the memory of our Professor Ramachandra Rao, who was a scientist, educator, and a leader, but also to celebrate the ideals of academic excellence, innovation, and mentorship that he embodied throughout his life. Professor Ramachandra Rao was and continues to be a beacon of inspiration for many of us in the field of metallurgy or material science and engineering. Throughout his illustrious career, he contributed extensively to the advancement of knowledge and technology, pushing the boundaries of what was known and possible. His pioneering research has left a legacy that continues to influence and inspire. It is impossible to talk about Professor Rao without acknowledging his outstanding contributions in the area of rapid solidifications, metallic classes, quartz crystals, and later on in the biomimetics. I think as an educator, Professor Rao was unmatched in his dedication. He spent his career's first job at IIT BHU, and then he came to as director of our laboratory, and he continued to be the director from 1992 to 2002. One of the most defining aspects of Professor Ramachandra Rao's career was his role as a mentor when he was in the lab. Basically, myself, Dr. Sinha, Dr. Srivastava, I think all were recruited in our National Metallurgical Laboratory that he had directorship. He believed in nurturing young minds and encouraging them to reach their full potential. He guided not just by sharing his knowledge, but by encouraging them to think independently and to challenge the conventional wisdom. His mentorship was characterized by patience, empathy, and a deep understanding of each individual's strengths and aspirations. He was not just a director, but a mentor, a guide, and a friend. Today, we stand here as a community, grateful for the many lives he has touched and the many minds he has shaped. It is fitting that we continue to honor his memory through events like this, where we can reflect on his contributions, draw inspiration from his life, further the fields to which he dedicated his career. Today, we are honored to have with us Professor Kenneth Kelton from Washington University, and he's going to speak on nucleation in liquids and glass, and their contributions echo the same spirit of curiosity, dedication, and excellence that defined Professor Ramachandra Rao's career. We are confident that today's lecture will provide us with new insights, inspire new ideas, and maybe some sparks will come up, just as Professor Rao would have loved. Before we proceed, I would like to take a moment to acknowledge Department of Materials Engineering at IISc Bangalore, Department of Metallurgical Engineering, and Professor NPGandhi Memorial Trust, and of course my own laboratory to make this event possible in every year. Today it is the 12th. I think your commitment is a reflection of the respect and admiration we all have for Professor Ramachandra. Additionally, I wish to express my heartfelt gratitude to each one of you present here today. Your presence is a testament to the profound impact Professor Rao had on your community and beyond. Whether you are a colleague, a former student, friend, or someone who has been inspired by his work, you carry forward his legacy in your own way. I think ladies and gentlemen, once again, I welcome you to this, and let us all remember that Professor Ramachandra Rao, not just for his incredible achievements, but for the values he stood for and the lasting legacy he left behind. Thank you very much, and welcome you again.
Thank you, Dr. Chaudhary. Thank you very much for the welcome address. Now I will invite Dr. Arvind Sinha, ex-chief scientist, CSIR National Metallurgical Laboratory, to elaborate on the genesis and significance of Prof. P. Ramachandra Rao Memorial Lecture. Dr. Sinha, please.
Thank you, Vikas. And good morning to Professor Kelton and Dr. Rao. And good evening to all the dignitaries who have joined from India. And on my behalf, I extend a hearty welcome to this Professor 12th Professor P. Ramachandra Memorial Lecture, which is third on its online international version. Our heartfelt thanks to Professor Kelton for readily accepting the invitation and agreeing to be the speaker of the day. This memorial lecture to celebrate the life and teaching of Professor Rao was jointly initiated by his students, friends, colleagues, and family members on the initiation taken by CSIR National Metallurgical Laboratory, Jamshedpur, NPGandhi Memorial Metallurgical Trust, along with Department of Metallurgy, IIT BHU, Varanasi, and Department of Materials Engineering, Indian Institute of Science, Bangalore. I extend my sincere thanks and regards to all my teachers at the Department of Metallurgy, IIT BHU, ISC Bangalore, and the then director and my friends and colleagues from NML for their encouragement and all-round support and time-to-time guidance to start and sustain Professor P. Ramachandra Memorial Lecture Series. Professor Ramachandra was a true visionary science leader who was worked on the scientific problem by diffusing the artificial domain walls like physical, chemical, engineering sciences, and the life sciences. He was a scholar driven by passion towards the science and solving scientific problems through his unique and innovative approach, which made his work outstanding and globally accepted. Just to introduce Professor Ramachandra Rao for the younger generation who might have joined online very briefly, he was among the most decorated contemporary Indian scientists. He was the fellow of all science and engineering academies of the country and the Third World Academy of Sciences. He was also a recipient of Shanti Saru Bhatnagar Award. He had been the president of Indian Institute of Metals, vice president of Indian National Science Academy, and Materials Research Society of India. He had an unique distinction of being the first student of Banaras Hindu University that not only served his alma mater on all the teaching positions like lecturer, reader, and professor, but also reached the height of being the vice chancellor of this great institute. Before becoming the vice chancellor of BHU, Professor Rao has served CSIR National Metallurgical Laboratory, Jamshedpur, from 1992 to 2002 as its director and added a dimension of material science and technology in this very lab that was well renowned for its contribution in Indian metallurgical industries ranging from mineral processing to the ferrous and non-ferrous sector. After completing his tenure as Vice Chancellor BHU, Professor Rao took over Defense Institute of Armament Technology under DRDO as its director and guided it to become the deemed university, and he became the first Vice Chancellor of this DRDO Institute. After his superannuation, Professor Rao joined ARCI Hyderabad as Raja Ramanna Fellow and continued there till he breathed his last. Professor Rao was among pioneers in the research of rapid solidification of metals and alloys. Through his innovative experiments he discovered many new intermetallics and metastable phases including design and synthesis of novel quasi-crystalline phases. He understood his new experimental results from the theoretical basis and developed the expressions for the energy, free energy of undercooled liquids and rapidly solidified alloys, and helped the global researcher to understand the formation of the metallic glasses. Diffusing the boundaries of engineering, physical, and life science, Professor Rao nucleated a biomimetic group at CSIR NML that has transferred a number of technology to the Indian biomaterial industry. Just to summarize, Professor Rao was not only an institution builder, he was an institution in himself. He was a man with scientific brain and loving heart, a rare combination, rare to found, but need of the hours. Thank you very much.
Thank you, Dr. Sinha, for bringing out such a good legacy of Professor P. Ramachandra Rao, and also the significance why this memorial lecture is so important to us. With this, I would like to invite Professor N.K. Mukhopadhyay from IIT BHU to kindly introduce today's speaker, Professor K.F. Kelton. Please, Professor Mukhopadhyay.
It's my proud privilege and honor to introduce the speaker today, Professor P. Ramachandra Rao Memorial Lecture. I know Professor Kelton when he visited Varanasi in the MOSPOC Quasi-Crystal Conference in 1989. And till then, I have seen him in many quasi-crystal and many other conferences. So let me read formally about his activity and his kind of achievement. Professor Kelton received his PhD in applied physics from Harvard University in 1983 and joined the physics faculty at Washington University in 1985. He is a fellow of the American Physical Society and have been an overseas visiting fellow at Churchill College, St. John's College, Sydney Sussex College, in Cambridge University, and a visiting scientist in the Joint Institute of Newton Sciences at Oak Ridge National Laboratory. He served as the chair of physics department at Washington University and was the inaugural director of the Institute of Material Science and Engineering. He has published over 300 scientific articles and is the co-author with Professor Lindsay Greer of Cambridge University of a book entitled Nucleation in Condensed Matter. His current research interests include nucleation process in liquids, gases, metallic glass formation, structural and dynamical and thermophysical properties of supercooled liquids, and the origin of liquid fragility and its relation to glass formation. I know from his work that he has made a phenomenal contribution in the quasi-crystal, especially titanium-based quasi-crystal. And right now, he is Arthur Holy Compton Professor Emeritus in the Department of Physics at the Institute of Material Science and Engineering, Washington University, St. Louis, Missouri, and USA. So without spending much time, I would like to request Professor Ken to start the memorial lecture. Professor Ken.
Thank you very much. Let me share my screen. Very good. So can everyone see this?
Yeah. Yes.
Good. Okay. Well, thank you very much.
Before we start, I will request all the participants to, if they have any question, they can write in the chat or raise their hands. We will take the questions after the lecture. Thank you.
Okay, thank you. It's an honor to be asked to give the Professor Ramachandra Rao Memorial Lecture. I met Professor Rao several times. The first time probably was in Varanasi at the meeting on aperiodic crystals and quasi-crystals. I knew of his work scientifically, but I had not met him before, and I found him to be, as everybody has said, very, very intelligent, very deep thinking, but also extremely gracious. He took me around Varanasi in his own personal car and took me to his house. We had a very, very good time there. So I have very fond memories of him. What I want to talk about today is a topic that does touch on some of his research activities, as I will tell you. I'm going to focus this on nucleation theory. I'm going to focus it on liquids and glasses, and primarily metallic liquids and glasses, although I'll mention a little bit about silicate glasses. And I want to give you sort of the state of the art of where we are in this field now. So let me find out if I can get a pointer here. There. Okay. So Professor Ramachandra Rao's interest I've put here, they're far-reaching. He did his PhD work with Professor Anantharam, and together they introduced rapid solidification into India, where they studied many things, including extended solid solution phases, metastable intermediate phases, metallic glasses. As you've heard already, he did a lot of work in quasi-crystals. He also did work on more traditional materials. He developed a lot of synthesis techniques, and he delved into fundamental understanding of the thermodynamics and kinetics of materials. My talk will focus on nucleation, but it will bring into the talk some of these areas that he himself had worked on. So let's talk about nucleation. We all know about nucleation. It's the first step in most first-order phase transitions, such as liquid solidification. There are typically thought to be two types of nucleation. There's homogeneous nucleation, which is random in space and time. It's a function of the material and the external conditions, and is difficult to study. Heterogeneous nucleation is much more common. It's random in time, but it's catalyzed at specific sites. Typically, those are impurities, container walls, things like that, oxide surfaces. But because of that catalysis, it's very difficult to interpret the results. What I'm going to talk about today is homogeneous nucleation, because there are techniques where we can probe that and avoid some of these problems that typically lead to heterogeneous nucleation. But one of the things that'll come out of this work is that distinction between homogeneous and heterogeneous nucleation is more blurred, I think, than we typically think. And I'll illustrate that later in the talk. One of the key observations that led to the study of nucleation was made by Fahrenheit, when he discovered back in the early 1700s that he could supercool liquid water. He could take it below its melting temperature and it would remain liquid, not crystallized. This indicates that there's a barrier to the formation of the equilibrium phase. And that is the key fundamental point from which we start to build nucleation theory. So it goes back a long ways. The first person to apply that, of course, was J. Willard Gibbs. And he developed what we now call classical nucleation theory by thinking about the thermodynamics of the formation of a cluster, in this case, a liquid drop, in a supersaturated vapor. He made several key assumptions. He assumed that the nucleus was spherical, he assumed that it was compact, and he assumed that it had a sharp interface between the nucleus and the original phase. Given that, he argued that the thing that you need to focus on is a minimum amount of work that's required to form this nucleus. And because of his assumptions, he argued that that would be given by a volume term, which takes into account the driving free energy, in this case, written as delta mu per atom, and a surface energy barrier term. This was the origin of the barrier that Fahrenheit discovered in his classical studies of water. Now, this is written in terms of N, but we often, I think, see it written in terms of the cluster size. And what I've done now is explicitly introduce the fact that delta mu is negative by taking the absolute value of, in this case, delta GV, and introducing a negative sign. So this term is negative and this term is positive. This term dominates for large cluster sizes. This term dominates for small cluster sizes. That means there has to be a maximum in the work of cluster formation, and we all know about that. You take the derivative, you find a quantity called the critical size for nucleation by setting the derivative equals 0, and from there you can reconstruct from here what the work of cluster formation is for a critical cluster. And so if we look at the amount of work that's required as a function of distance and size of cluster, It first of all increases due to the surface energy penalty, and then it begins to decrease due to the larger contribution from the volume for energy. Gibbs said that this was the relevant quantity, and if you want to look at the probability of having a fluctuation leading to nucleation, then you just take a Boltzmann-like factor of the work of cluster formation normalized to KT. That's the thermodynamic model of nucleation that we still use. The kinetic model of nucleation came later. Gibbs was the late 1800s, Vollmer and Weber were the early 20s. And what they said was that you have clusters growing kinetically by either having a single atom attaching from the vapor phase or that atom detaching from the cluster. The fact that they can attach and detach illustrates the stochastic, the randomness that is inherent in nucleation processes as opposed to growth processes. They said that this occurred by a single atom at a time, and so they expressed this in terms of rate equations, where we had a cluster of size n-1, you had a single atom join that cluster, and with a forward rate constant, it would become a cluster of size n, one larger. But then you could also have it leave the cluster and go back to the original cluster plus the single monomer. And they developed this for every single cluster. So what you end up getting is a cluster population. And here's an illustration of that. This is the log of the cluster population as a function of cluster size. And you end up having different populations for different clusters, and generally the population decreases as you go to larger cluster sizes. From here, the nucleation rate is going to be the flux past a given cluster boundary. And that's going to just be given by this. And this is an important point. This points out that the nucleation rate is in general a function of time and a function of the cluster size at which you measure it. All of these are considerations we typically don't think about, but they are important, as I'll show you later. Turnbull and Fisher were the first to try to take these ideas and apply them to condensed matter. And what they had a problem with was, how do you take into account the addition or subtraction of a cluster? And they argued that it really is expressed in terms of the diffusion coefficient in the parent phase. So in this case, the liquid. So you have a liquid atom joining the cluster to become part of the cluster, or you have an atom leaving the cluster to become part of the liquid. So that's analogous to what the Vollmer-Weber kinetics were. And in fact, Turnbull and Fisher kept the same assumption, that you had a single atom joining and a single atom leaving at a time. They then used an expression that had been derived by Becker and Doering earlier in 1935, where they looked at the question of what is the correct distribution to describe the nucleation rate, and they argued that it's a steady state cluster distribution, from which they could get the steady state nucleation rate in terms of a factor Z, which is the Zeldovich factor, which is shown here, and it typically is between 0.1 and 0.01. It doesn't vary much. The forward rate constant, and then the Boltzmann factor term. So that means then, if you look at this term, this is just the equilibrium concentration. So this, they said the steady state rate was equal to this factor Z multiplied by the forward rate constant multiplied by the equilibrium concentration. And if you go back to Turnbull-Fisher, that's where the forward rate constant is. So it seems like we have everything all now together where we can describe the nucleation rate. And together, this is called the classical theory of nucleation as it's applied to a variety of different systems. Now, one of the key factors you need is the deriving free energy. You would actually have to calculate it knowing the enthalpy, the differences in specific heat between the liquid and the crystal phase, but often those are not known. So often what's done is to use just the leading term and assume that delta Cp is effectively zero. This is sometimes called the Turnbull approximation. But there have been many other proposed approximations, and I wrote an article many years ago where I looked at those. I just pick out three here. This is probably one of the most commonly used. It's Thompson and Spoppen in 1979. And the reason it's used is you don't really need anything other than the heat of fusion and liquidus temperature. You don't need to know anything about delta Cp. But two that turned out at the time I wrote this article to be very good were both developed by Ramachandra Rao and his group. And these you do need to know the specific heat, but you only need to know it at the liquidus temperature, which is relatively easy to measure. If you compare these expressions, here I've compared a lot of other expressions, but these are the actual driving free energy measurements as a function of temperature for indium, the dots. Line 1 is the Turnbull approximation, and it's not too bad, but as you get deeper and deeper in supercooled liquid, it becomes worse. But 7 and 8 are right here, and they fall right on the data. So these are two actually very, very good approximations. And if you didn't have any data, I would use those. However, now it's possible to measure delta Cp relatively easily as in supercooled liquids on the International Space Station using a facility that I will talk about at the end of my talk for another reason. Now we have to have estimates of the interfacial attachment kinetics. You need both the thermodynamics and the kinetics. As I said, Turnbull and Fisher argued that the kinetic rate should be proportional to the diffusion coefficient in the parent phase. How do we get that? Well, if we're thinking about a liquid and sometimes a glass, you could argue that you could use the Stokes-Einstein relation. The problem with that is that certainly for glasses, the Stokes-Einstein relation is not valid. It breaks down as you go deeper into the supercooled liquid. And even if you get into the liquid, it's possible to go past the point where it begins to break down. So this is probably not the best way. Another way is that because in classical nucleation theory, we often talk about nucleation and growth, but there really isn't a cluster size at which nucleation stops and growth begins. It's a continuum. And you can measure then what the growth rate would be from that continuum, and you get an expression like this. So you could measure the growth rate, and from there you could calculate the diffusion coefficient. But for glasses, there's a better way. And this was first developed for silicate glasses. So let me talk a little bit about silicate glasses. Silicate glasses, it's a very big industry, both for the glass as well as for the glass ceramics that you make from the silicate glasses by controlled heat treatments. Since you want to make a desired microstructure, you need to know the nucleation rate and the growth rate. So places like Corning spend huge amounts of effort to try to measure this. One of the interesting things about silicate glasses is you can get very accurate measurements of the nucleation rate by doing what's called a two-step annealing treatment. And that is you take the glass, you anneal it, you heat it for some period of time at a temperature where the nucleation rate is very high and the growth rate's very low. And then you increase the temperature quickly to a temperature where the growth rate's very high, but the nucleation rate's very low. And what that allows you to do is to grow all of the nuclei that you produced on the first heat treatment. So you can do this very accurately. Then you just count the number of nuclei that are present after the second treatment. If you looked at the number of nuclei as a function of time, what you would expect from Becker-During is to get something like this. This would be the expected steady state nucleation rate. The numbers should increase linearly with time since the nucleation rate is constant. But instead, what you find is that very often the nucleation rate, which is given by the slope, becomes very small initially, and it increases with increasing time. This is nucleation time at the first treatment, the nucleation treatment, and eventually becomes steady state. It almost, to first order, looks as if you were far beyond what is called the induction time, which is the extrapolation of the steady state rate back to the time axis, and it's called theta. It almost looks as if the number of nuclei would be the steady state rate multiplied by the time t minus that induction time. That's a very low order, but that's what it looks like. This induction time is going to be critical, and I'll talk about that in the next slide. And this is a technical point, but one that's often overlooked when people are making these measurements in the silicate glass community. This is the induction time at the growth temperature, and that gets more complicated, but it's an important thing to know if you're going to be trying to use this to make some measurements of the kinetics. Now, why would you expect to have a behavior like this? Well, I can explain it qualitatively in this way. Remember that I said that the nucleation rate is proportional to the forward rate constant times the equilibrium distribution. So if you think about quenching a glass, what you're going to do is take a high temperature distribution, you're going to quickly lower the temperature, and you'll end up getting that distribution at the lower temperature. It will want to change. For example, if I have a distribution at 430 Kelvin from a quench, and I quench it to 390, it will want to have this distribution, not that distribution. The only way that that can change is through the bimolecular rate kinetics. So that takes time. So initially, the nucleation rate would be the critical size at the lower temperature, if we're measuring it at 390, multiplied by the equilibrium distribution. The equilibrium distribution should be here. But actually, when you start, it's way down here. So you have orders of magnitude lower nucleation rate. As you let it proceed, this distribution will relax to the distribution at the temperature at which you're doing the nucleation measurement. So it's the fact you're quenching the liquid quickly to form the glass that gives rise to this effect. This time, which I call the induction time, is related to this relaxation time of the distributions, which I'm going to call tau. Now, I don't want to go through the mathematics, but there is a solution for this, which is first given by Kenneth F. And he showed that the nucleation rate as a function of time is given by the steady state rate multiplied by this sum. And in particular, he showed that if you look at the number of nuclei produced and you normalize it to the steady state rate and this transient time, which is that relaxation time, which I've labeled tau k, then you get an expression like this. What does that mean? Well, if you look at it, it says that if I make this plot the number divided by the steady state rate multiplied by the transient time as a function of t over tau k, I get a universal curve. So what he predicted a universal curve, and if you go back and look at a variety of different silicate glasses for different nucleation temperatures, you find that they do indeed follow that curve. So that's a very powerful theorem, a very powerful expression. Embedded in this is this induction time, or transient time, excuse me, which is related to the induction time by this simple expression. And he shows in his calculation that this transient time is given by this. And I've highlighted the key factors. The transient time is related to the inverse of the forward rate constant. And the transient time is directly related to theta. So that means that I can use this measurement to calculate the induction time, or to the forward rate constant. And when you do that, it's just a matter of taking these two equations with that one and doing a little bit of algebra. You get to this expression that the steady state nucleation rate multiplied by the induction time, if I plot that as 1 over t delta GV squared, I should get a straight line. Okay. And this is one of the reasons I wanted to introduce this, because this has been hearkened and discussed for 40 years that this points to a failure in the classical theory. Let me explain what that means. So here's that equation I showed you. Here are two different glasses, both barium silicate glasses, but different stoichiometry. These are the measured values that you have for the steady state rate and the induction time from those two-step annealing treatments. In both cases, you find out that at high temperatures, you can get a reasonably straight line. But as you go to low temperatures, which is going this direction toward the left, it departs radically from a straight line behavior. Now, since this is a log, we're talking of orders of magnitude departure from a straight line behavior. These are two examples. However, this has been observed in multitudes of silicate glasses. And so, again, if you go to the literature, up until about 2 years ago, you could find many, many theoretical explanations for why the classical theory was failing. But it turns out it's more complicated. Here are the data measured at the lowest temperature in that previous study that I showed you for these silicate glasses, measured at the lowest temperature. Well, it kind of looks like what I showed you, the number versus time, and this is nucleation time in days. Starts off low and then it gets to a steady state value. You extrapolate that back to the axis, you get the induction time, and the slope of that straight line is the steady state rate. But the problem is these data fit into that data point if we extend the amount of time that we measure at the nucleation temperature. So now instead of 0.8 days, these data go to 140 days. These original data, which were argued to show the induction time and the steady state rates, really are only a tiny fraction of the whole relaxation behavior. And this is a problem with this method. Basically, these curves are self-similar. And so it's very difficult to tell when you finally reached true steady state. But if you take these new data, the steady state rate in the old data, these red data here, was 48 per millimeter cube second. The new data, the steady state rate is an order of magnitude larger than that. The induction time in hours in the original data here was 5.9 hours. In these new data, it's a factor of 100 larger than that. So if you take these data and plot them, there's this new data point for this temperature. Here are the old data points that I showed you. At high temperatures, the old data points and the new data points agree. At low temperatures, however, this one is orders of magnitude larger than the original data point. And now we have perfect agreement with classical theory prediction. So even though it's been in the literature for 40 years, it turns out that this failure of the classical theory is actually an experimental artifact. And this is extremely important to the silicate glass community. As I mentioned, they need to know these nucleation rates and these induction times very accurately to develop controlled microstructures for glass ceramics. This experiment indicates that probably every existing experiment in silicate glasses for low temperatures is wrong. So they need to go back and re-examine this. But the classical theory didn't fail. People are always trying to find places where the classical theory failed. It didn't fail here. But there are some questions that we can ask about the fundamental assumptions within the classical theory. And one way we can look at that is molecular dynamics. So the thermodynamic assumptions, again, we have a sharp interface between the cluster and the liquid or glass. We assume a macroscopic driving free energy to describe the change in chemical potential for a single atom joining a cluster. That's possibly questionable. And as I'll point out later, there's no inclusion of the fact that you might have ordering in the liquid and glass and what that might do to the nucleation barrier. In the kinetic assumptions, we have a single pathway for nucleation. This is the Vollmer-Weber bimolecular kinetics. And another question is that the classical theory assumes interfacial kinetics. But there are many cases where you might want to look at long-range diffusion during the nucleation step. So these are some of the key kinetic assumptions that need to be evaluated. These are some of the key thermodynamic assumptions that need to be evaluated. Let's take the first question of a sharp interface. These are some molecular dynamics for nucleation in an aluminum nickel zirconium liquid. And what has been defined here is what's called an index of crystallinity. It's defined in terms of bond orientational order parameters, if you want to see the equation. But what it means is it's an order parameter. It has one value, a high value, if it's in an ordered crystal, and it has a much lower value if it's in the liquid. And shown here is a range of values. 120 would characterize the center of this nucleating cluster, where you can see the order pretty evidently with your eyes. This is a highly ordered part of the cluster. 50 is what it has in the liquid, which is shown around here. Now, two things you find out from these calculations immediately. The cluster is not particularly compact. I mean, you could argue it's somewhat compact, but this is a large cluster. If you look at small clusters, it's very non-compact. It's almost fractal in its boundaries. The other thing is, it does not have a sharp interface. You can see there's a gradation in going from the center of the cluster to the edge of the cluster. So there's a continuous ordering process as you go towards the center of the cluster. So that Gibbs assumption is incorrect. This has also been found in studies of crystallization in colloidal suspensions. This is a rather old paper, but it was a classic paper that showed from those studies, again, the non-compactness of the clusters. Okay, well, it turns out there is a theory that can handle this. It's called the diffuse interface theory. Basically, what does it mean to have a diffuse interface? And I show it schematically here, where you have periodic arrangements of atoms, and as you get closer to the liquid where you don't have periodicity, that periodicity in the cluster starts to decay. That means then that Gibbs' idea of having a sharp dividing surface isn't correct. You can't say, here's where the surface is and here's where the volume is. Instead, you should focus on the total free energy, and the total free energy will have some profile where it will go from the free energy of the liquid to the free energy of the solid. But in the process of crossing the interface, there'll be an increase in the free energy. If we knew what this profile, what this curve was, it would be trivial to calculate the work that's required to form a cluster of a given size. But we don't know what this profile actually is. Independently, Franz Schwappen and Laszlo Granashi, back in the early 90s, came up with a solution. What they said was, well, we don't know what the profile looks like, but let's at least assume that we have a diffuse interface, and they approximated the free energy by a step function. Now, I don't want to go through all the mathematics here, but you can find it in Schwappen or in Granashi's papers. One key point that comes out of this diffuse interface theory is an explanation of something that David Turnbull found when he first started looking at nucleation of mercury in mercury. What he found was that to fit the nucleation data that he was experimentally measuring, he had to assume that the temperature dependence of the interfacial free energy was greater than 0. Now, if you think about that, the interfacial free energy is a free energy. So it should have some delta H minus T delta S term. So it should have a negative temperature dependence, but it didn't. It had a positive temperature dependence. And this has been found over and over and over again in other liquids, as well as in silicate glass experiments. The diffuse interface theory gives an explanation for that, which turned out to be exactly the one that Turnbull argued sort of just by physical insight. This arises because of the presence of a diffuse interface. Turnbull called it a neg entropy effect, where you were overcompensating for the entropy change, and that's effectively what the diffuse interface tells you. If you wanted to do experiments or analyze experimental data with this, you can do it because they've developed an expression, this is primarily due to Laszlo Granashi, for an expression for W star. It's a little complicated because these delta H zeros and delta S zeros is the width of the curves for independently for H and for S. So as you go from the liquid to the cluster, that's the size of those clusters, and that's of that curve. That's what that is. But if you knew that, then you could calculate the nucleation rate much better than you can calculate from the classical theory. So there is an alternative to the classical theory that's quite tractable. Now let's go back and look at the order through the interface. Here now, what I've done is I've shown the order parameter as a function of distance. Here is the case for a large cluster. This is a very large cluster that's well past the critical size at the temperatures in this MD simulation. And you can see that at the center, the order parameter is equal to that of the ordered crystal, shown here by the dashed line. And then as you go towards the surface of the cluster, it decays and eventually becomes the order parameter of the liquid. That's what I showed you before schematically or pictorially. One thing that comes out of this calculation, however, is that if I start decreasing the size of the cluster relative to the critical size, so these are all still larger than the critical size, but they're approaching the critical size, you still have the decay from the center to the liquid, but as you go to smaller and smaller clusters, you never get to the ordered state of the crystal. So for small clusters, the whole cluster is disordered, which means that initially when we form nuclei, those nuclei are very disordered. They don't look like the crystal phase that they're developing into. As they grow, they do. These are MD simulations. These are some earlier calculations from a density functional approximation. And you see that everything here is in normalized units. So basically, as R sub S increases, you're getting a larger cluster, but they have it normalized to different things. But the key point is that as you have very small clusters, the order parameter never gets to what it should be in the crystal, which is up here. As you increase the cluster size, it gets closer and closer. And then if you get to, in their case, a very large cluster size, it still decays through the cluster because that's reflecting the diffuse interface, but at least in the center of the cluster, you have the ordered crystal. So these two are identical. And they both indicate strongly that the thermodynamic assumption in the classical theory is wrong. Now, what about the kinetic model? The kinetic model assumed that we have single atom additions and subtractions to the clusters as they grow. I've illustrated that here in a different way. There are single atom attachments and detachments. There are diffusive type jumps onto and off of the cluster interface. But the problem is, if you look at the densities of the liquid and crystal, this is the liquid, this is the crystal in an MD simulation, there's very little room for jumping. So the idea that Turnbull Fisher have, where you have a jump going from the liquid to the crystal, seems problematic. Now, one of the ways we can investigate that is to put in seeds. And basically what you do is you take a liquid like this, you carve out a piece of the liquid, and you put in a crystalline seed. And then you look to see whether that crystal seed grows or shrinks. And from that, you can determine the critical size. But you can also look at how the atoms are attaching. So this is, again, nucleation I'm using this one to illustrate, but this has been observed in other metallic liquids as well, including monatomic nickel. So you add this critical seed, and then you watch the shrinkage and growth. And what you find out, I'll show you this in a second, but what you find out is that atoms don't just attach one at a time. They attach and detach collectively. So more than one atom. Here's an illustration. Here's a case, this is an MD simulation showing the change in index of crystallinity as a function of time. It's MD, so these are in picoseconds. And you can see that this crystallinity of this particular atom, these numbers represent different atoms. It sort of stays for a while in the liquid phase, and then it decides it's going to join the cluster, and then it does so here. So it quickly increases its index of crystallinity to match that of the crystal phase. This shows you nearest neighbor atoms of this atom. And what you see is that they all act collectively. So this one they're all in the liquid phase, and then they start to join the cluster, and they join the cluster at the same time. You can also see it in detachment. Here's a case, remember this is nucleation, so you can have atoms attaching and detaching. So here you can see it during detachment. Here's the single atom that's detaching. It's different from this one that's joining, so it picks a different atom that's detaching, and all of its nearest neighbors. And so they, again, detach collectively. This is also true for homogeneous nucleation. That was seeded nucleation. But molecular dynamics modeling now is you can look at such large ensembles that you can actually see nucleation events, something we couldn't do very well in the past. And here's a case, a single atom. It joined a cluster, and then it left that cluster. And then it diffused around in the liquid and then joined a different cluster. Here's the case for its nearest neighbor atoms. Here's the joining, and they all do it together, and they all leave together. But then, of course, now they're separated, and they're in the liquid, and they diffuse around. And when they join another cluster, they don't do it together. They don't follow each other. But while this atom was moving around in the liquid, it found other neighbor atoms. And when it started to join the cluster, they all joined together. So to illustrate that, here's a situation where the atoms, these blue atoms, are next to a cluster. They join the cluster. Here you can see that they're part of the cluster. Here I've labeled those atoms in white so you can see them. And they stay in the cluster, and then the cluster continues to grow, and so they're embedded in the cluster. When you look at how these atoms are joining, they're not doing it by diffusive jumps. They're doing it by changes in orientation to basically match the order of the crystal. So they're rotating, they're moving around a little bit, but they don't jump to join the cluster. This has been observed in these studies. It's also been observed in other studies, other MD studies. And collectively, what they say is that the kinetic processes are in conflict with the assumptions of the classical theory. So taken together, what these say is that basically all of the assumptions in the classical theory are incorrect. We know how to accommodate the diffuse interface. The diffuse interface theory actually works quite well. We don't yet know what the consequences are of this change in kinetics. It may not be evident. It may be that those subtleties you can't see, but at least fundamentally, those assumptions are highly questionable. Okay, so that's sort of critiquing the classical theory, but we can go beyond that and look at what is a major effort now in understanding nucleation processes, which is multi-step processes. And I'm going to show you some of the work we did, and then illustrates with some other. But to show you that work, I need to talk a little bit about a couple of things. One thing I need to talk about is how we make these measurements. We make our measurements in something called an electrostatic levitator. And here's the one that sits in our lab. You can see the blue in here. That's not just for photogenic reasons. The way this works is we have two sets of vertical electrodes with about 10,000 volts applied to that. We have two sets of orthogonal side electrodes with a smaller, about 3,000 volts applied to that. All of those voltages we can control with a computer. When we put a sample, a metallic sample in there, we end up getting charge separation because of the very high voltage on the top electrode and bottom electrode. And so that causes the sample to be levitated. We then look at a high intensity LED, which is what you see here. This is a high intensity LED, and we look at the shadow of the sample on something called a position sensitive detector. We have two of these that are at right angles. They're orthogonal to each other. And so from that, we can get, from the shadow, we know exactly where the sample is sitting, the X, Y, and Z coordinates of where the sample is sitting. We then use active feedback, computer active feedback, to control the voltages to keep it sitting there. We can do that to keep the sample stability to about plus or minus 10 microns. And these are small samples. They're about 3 millimeters in diameter, but we can keep them very highly positioned. The chamber is under high vacuum. We use lasers to heat the sample once we have them levitated. Because we're heating the sample, we have to have high intensity UV lamps on the sample to restore charge, because when you heat the sample, you're going to have evaporation and that will carry off charge. So we have to replenish that charge. But we can do this, and we can do processing in a very stable way. With this apparatus, we can measure supercooling, growth velocity, density, viscosity, and by taking this to a synchrotron, which there's one near us in Chicago at the Advanced Photon Source, we can do synchrotron scattering measurements. And it's a very simple technique. You just have a very high intensity, very high voltage, 130 kiloelectron volt beam that punches right through the sample and gives us a scattering pattern, which we record on an area detector. This is a very good way to measure diffraction data. We've measured quite a lot of it, and it's very high accuracy, very low noise data, because there is nothing else to scatter from. So it's a very low noise environment. And so you can end up getting data that look like this, where we can follow ripples in the G of R out to very high values of R. So the other thing I need to introduce is something that Ramachandra Rao would have been quite familiar with, which is quasicrystals. In 1984, Dan Sheckman discovered an interesting set of electron diffraction patterns that seemed to violate fundamental laws of crystallography, in particular this one. What he found was a diffraction pattern with 10 spots around a central spot. 10 is a multiple of 5, and it is well known that 5-fold symmetry is incompatible with translational periodicity. This led to an entirely new field, the field of quasicrystals, and Dan was given the Nobel Prize in chemistry for it in 2011. It's often thought that these quasicrystals are disordered high-temperature materials, but this is one that was grown by Fisher and Canfield, a quasicrystal to macroscopic size, and you can see it's a beautiful dodecahedron. If you looked at the scattering from this particular sample with synchrotron X-ray scattering, you would find that this has higher quality than the single crystal silicon they use for monochrometers. So it's not a disordered structure. It's an extremely ordered structure. But I need to use this because I want to combine those 2 slides I showed you to look at a titanium zirconium nickel liquid. Here's that liquid processed in the ESL that I showed you. We've heated the sample well above the melting temperature. We turn off the laser and it starts to cool. It well into the super cooled state. It then has a sudden release of heat, a sudden increase in temperature as it begins to nucleate and grow, releasing the heat of fusion. But in this particular case, this is called a recolescence. So it had a recolescence, first recolescence, and then there was a plateau, followed by a second recolescence. Whenever you see this, it's a good illustration of metastable phase formation. So what we were doing was forming a metastable phase first, followed by the formation of the stable phase. Because we were using such high intensity X-rays, we were able to trigger on the first recolescence. And even though this plateau is only 2 or 3 seconds long, we could get a complete diffraction pattern. And what we found was that this first recolescence was to an icosahedral phase. The second recolescence was to the equilibrium phase that we expected, which was a C14 Laves phase, complicated intermetallic. If you looked at the liquid as a function of decreasing temperature, so before we had recolescence, here's what it looks like. This is the structure factor as a function of inverse momentum transfer. The thing to notice, of course, it gets sharper. You can't really see that because I've offset the curves. But the reason I offset the curves was so that you can see this little shoulder that's developing here on the high Q side of the second peak. By taking the Fourier transform of this, we can get to the pair correlation function. By integrating it under the first peak of the pair correlation function, we know that the coordination number is 12. If we look at any possible 12-fold local clusters, and we looked at, I show it here for FCC and the icosahedron, but if you look at it for HCP, and we even looked at it for BCC, which is not 12 coordinated, what you find out is that the only cluster that gives rise to this shoulder that's developing is the icosahedral peak, or icosahedral cluster. So this is a signature of icosahedral ordering in the liquid, which I speculated could be the reason for the formation of the metastable icosahedral phase. And in fact, if you measure the interfacial free energy between the I phase and the liquid from nucleation measurements, it turns out to be 0.06. That's very small. That's much, much smaller than people normally see in liquid to crystal transformations. But even more compelling to me was if you looked at the critical cluster diameter that you could calculate, knowing the driving free energy and the interfacial free energy, it turned out to be about 3.5 nanometers. If you estimated the coherence length from the liquid structure, that turned out to be 2.1 nanometers. These are all rough estimates. So basically, they're the same. So what this says, coupled with the low interfacial free energy, what this says to me is that the icosahedral ordering in the liquid has lowered the nucleation barrier for forming the I phase. But the fact that you have a length scale where it starts to nucleate, says that within this liquid, you have certain regions of icosahedral order. And then that raises the question, is that homogeneous or heterogeneous? Because you've got certain sites in the liquid that are catalyzing the formation of the phase. And I would argue that that's blurring the distinction between homogeneous and heterogeneous. Okay. Now, the other thing that this is much more recent data that we're just finished, and we're have a manuscript in preparation for publication. We looked at the eutectic nucleation of zirconium-82 platinum-18. That's right here. Why did we do that? Well, if you go to the literature, and I didn't know this before about a year ago, if you go to the literature and try to see what people know, what we know about eutectic nucleation, you find there's virtually nothing in the literature. We understand quite well eutectic growth. We teach that in our graduate kinetics classes. But nucleation, nobody has done any experiments on it. There's been a little bit of work on eutectoid formation, but there you find out that you get different answers depending on which papers you read. One paper might argue that based on the experiments, that there's nucleation of a metastable phase first, which then subsequently transforms to the eutectic phase mixture. One paper might argue that you nucleate one of the two phases for the eutectic, and then that catalyzes the other. But there's really no clear evidence of any of that. And here's some experimental evidence, at least in this one system, where the first phase to form was a metastable quasicrystal. Again, we know that this particular liquid has a lot of icosahedral order. We've measured that from the liquid. Also, it has been known for about at least 15 years that if you quench this very rapidly, you will form a icosahedral quasicrystal. It's not a very good one. It's a nano-size icosahedral quasicrystal. But it's all consistent, and it seems to be that in this case, eutectic nucleation proceeds first by the nucleation of a metastable phase, which then transforms to the equilibrium eutectic phase mixture. So what's the role of icosahedral ordering liquid? Well, I've given you my understanding is that it's because we have the structural ordering of the liquid is catalyzing the nucleation. But you could argue that it can have a more general influence on nucleation, where it actually helps other phases in addition to the quasicrystal. And that's been argued by Tinwell and Frenkel and Tanaka, where they argue that nucleation is a two-step process. First, densification of the liquid, followed by ordering of that region of the liquid. And that could also be supported by changing in the kinetics. This is a recent paper from Pastorel's group in France, where they did MD simulations, and they found all the MD simulations show that when you get regions of icosahedral order in a liquid, they're slow. What they said was that what they did was they correlated where nucleation occurred, and it always occurred in these slow regions. The other regions are just too dynamic for nucleation to occur. So there's another reason icosahedral order might lead to nucleation and growth. So it could be a very complex process with a variety of different reasons. I'm going to skip this because I'll just briefly say that you can measure time-dependent nucleation in metallic glass. This should look similar to what you saw before. The one thing, it also scales to the Kashchev approximation. And from this, we can calculate the interfacial free energy. And it's very low. It's extremely low. It's almost at the end of the talk. In addition to coupling to order, you can have coupling with other phase transitions, first order phase transitions, for example. There are many cases of those, even coupling with second order phase transitions. Okay, all of these that I've shown you are examples of multiple pathway nucleation. I've shown you 3 examples here, which are two-step nucleation processes, but there are many others. And there's a paper by Dioro where he's categorized these in terms of the energy landscape and the influence of dynamics. And he's gone through many of the different cases you can have, including cluster-cluster interactions, but including the two-step phases I've talked about and other kinds of intermediate stages that you could get. Okay. So the last thing I want to briefly talk about is that CNT is an interface limited theory, but in many cases we know that long-range diffusion should be important. And how do you do that? Because I've mentioned a couple of times Cluster growth is stochastic. It's diffusion-like. Long-range diffusion is, of course, diffusion. It's stochastic. And so if you want to solve this problem rigorously, you have to come up with an analytical way to couple two stochastic processes. And I don't know how to do that. So what I did was I developed a very simple model where I looked at the cluster, a region around the cluster, and I looked at atoms moving into and out of the shell region from the parent phase, and then joining and leaving the cluster. The thermodynamic model for this is very simple. You basically assume the Gibbs model, but you have to include an entropy term because you're taking atoms from far away and you're localizing them to a shell. That's this term. The kinetic model is a little more complicated because now you have to look at the population not only of the cluster size, but of the number of atoms in the shell region. That's shown here vertically. And so, in other words, you have to have at least one atom in the shell region before you can combine with the cluster to give you a cluster of a larger size. So this staircase kinetic model is characteristic of this. You can solve this model with computer calculations, and it predicts, one prediction is that you end up getting an enhanced solute concentration in the parent phase near the precipitate, if you're thinking about single component precipitation. That's contrary to what we normally think of in growth, where you would see that there's a depression of the solute concentration next to the growing precipitate. But this is nucleation, not growth. Nucleation, since it's stochastic, you can have fluxes coming from the cluster into the shell and from the parent phase into the shell, and they're all coupled. And this observation from the computer calculations that I did has been supported by kinetic Monte Carlo calculations. The other thing is that as you make the diffusion slower, then you can suppress the nucleation rate by orders of magnitude from what you would expect in steady state. Steady state classical theory is interface limited. So those kinetics are much, much faster than those kinetics are limiting. The diffusion kinetics are faster. But if you move it down to the point where the diffusion rates become limiting, then you end up depressing the nucleation rate. That also agreed with kinetic Monte Carlo calculations, but we wanted to check it experimentally. And so the quiescent conditions in microgravity allowed this to be checked. This is an example of the ISS EML on the European Space Agency, European Space Agency EML on the ISS. What is EML? It's electromagnetic levitation. Here, what you do is you have an RF coil, RF field that creates a magnetic field in the sample that's levitating between the coil, and that in turn creates eddy currents in the sample, which creates an opposing magnetic field, and so it levitates. If you do these experiments on Earth, however, you have generally one coil, and you have a problem because you always have to supply enough power to keep the sample levitated, in which case it's very difficult to cool the sample. But in space, you don't have that problem. This particular facility has two separate coils. One is a quadrupolar coil, and that's used for positioning. And one is a dipolar coil, and that's used for heating. And you can decouple those two. You don't need much positioning force in space in microgravity to keep the sample. So that means you can take the sample to very low temperatures by turning down the heating. You can also increase the positioning power if you want to. And what that will do is cause the sample to stir. And so by using this, you can get controlled stirring. You can also measure then maximum undercooling and growth conditions under controlled stirring. You can measure thermophysical properties such as specific heat, and you can measure electrical resistivity. The latter two have led to some very interesting observations as well, but I'm not going to talk about those here. This is the key result. This is vitrolloy 106A, which is a liquid that forms a bulk metallic glass. To crystallize it requires long-range diffusion. So we see, as I predicted, if we have a very low stirring, then what you're going to have is diffusion is going to be dominant during the nucleation step. And so you'll have a low nucleation rate and you'll have a lower value of A star because this won't change. If you increase the stirring rate, then what happens is you bypass the need for diffusion. You're actually stirring the system, so you're bringing atoms to the cluster that way. and you end up seeing an increase in the nucleation rate. And this is consistent with the coupled flux model. So I'm going to leave this talk. I don't know if you're going to post this, but if you want to, you have my permission. And I've left a few possible useful references if you want to follow up some of these things on multi-step nucleation and so forth. But I'm going to conclude now, and looking at my clock, I'm maybe 4 minutes over. So I'll just leave this up there and we can then have questions.
Thank you. Thank you, Ken, for your wonderful and illuminating lecture. Would you like to take some questions if there are some questions from the audience?
Yes.
So I think the paper is open for discussion. If anybody has any questions or comments, please raise your hands or put the chat box.
Yeah, good evening, Professor Kelton.
Hello.
I'm
Shastri, yes.
Shastri.
Yeah.
I don't know whether I missed if you had already explained. I wanted to know the difference between induction time and usually known incubation time. You are using it.
Typically, those are used interchangeably often. I tend to call them induction time. There are different times that people have defined for this particular experiment. There's another time that's the time to steady state and things of that sort. But when I use induction time, it typically means the same thing to me as incubation time.
Okay.
As long as it's measured in the same way. Now, somebody else might have a different definition of induction time, but as long as it's measured at that intercept, then I would use it the same way.
So you extrapolate and find the intercept, and that's what you're.
That's the induction time. That's correct. Yeah.
It was a very illuminating talk. Thank you so much.
Thank you.
Ken, I have a question.
Yes.
Yeah, before anybody else is asking. You talked about the icosahedral cluster and seems to be in the titanium base. You demonstrated that it is metastable because the first recollections related to the icosahedral kind of quasicrystal formation.
That's right.
And second recollections transforming to Laplace-like phase, right?
Yes.
Now, the reason maybe I have missed it, I have two questions in this respect. And nowadays, I mean, it is known also for quite some time that some of the quasicrystal system, you get from the liquid itself, you get a stable quasicrystal. And so that means that icosahedral phase which is there, and that is in the binary and ternary. For a typical example of aluminum, iron, copper, aluminum, palladium, manganese, and even the rare earth magnesium alloy and titanium based system as well. So the question is that what is that in some cases that gets stabilized and gives rise to a stable quasicrystal, and some cases it doesn't give. That's my kind of curiosity.
That's a good question, because in fact, in this particular alloy, that the titanium, zirconium, nickel, there also is a stable icosahedral phase. But what happened in this case was we supercooled the liquid to the point where it was in the equilibrium phase field of the C14 Laplace phase. That's what should have formed in equilibrium. But we hadn't cooled it deeply enough that we had entered the region of quasicrystal stability. We were still in the C14 stability range. And instead of nucleating the C14, it nucleated the quasicrystal. So that's why it was metastable. It wasn't, we weren't in the right temperature range for it to be in the stable phase. But if you take that same alloy and go deeper into temperature, then you can form a stable quasicrystal. And in fact, we did an experiment many years ago now where we showed that it was reversible. So if you heated it up from the quasicrystal into the C14 phase field, it transformed to the C14. If you then lowered the temperature and annealed the solid in the quasicrystal region, it transformed back to the quasicrystal. So it was actually a reversible transformation. So it depends on the temperature you are, it depends on the interaction and things of that sort. But anyway, so I think that's the reason.
I think there is one question in the chat box. Could you look at the chat box question, Ken?
Okay, let me see.
Otherwise,
Okay,
I can read it.
I talked about the models for nucleation theory from liquid to solid state. Is the model applicant for decomposition where we observe homogeneous nucleation of a phase that has a different composition in the solid state? So if the question means, is the theory applicable for solid-solid transformations?
Yeah.
Which is what I'm interpreting it to mean, then the classical theory is commonly used there. Yes, I think so. I think that all of the questions, however, about the interface and about the thermodynamics, the kinetics, would have to be examined because I think, again, you've got a dense solid forming another solid. So it's quite possible you could have some problems with a hopping mechanism there as well. And also, if you ended up having a different composition, then you're also going to have long-range diffusion effects potentially. And we normally think about that for growth, but at least the calculations I presented indicate that it could be important there as well. So I think this is a wide open field. I think up until now, we've sort of used the classical theory, everyone, including me, have used the classical theory. And I think now as we develop new tools, both experimental and modeling, I think it's time to go back and look at some of these points.
Sure. Yeah, I could see many distinguished scientists who have joined here. And if they like to have any questions or students, if you have any questions, for example, Professor R.K. Mandal, I could see he has worked on nucleation theory, and also Professor Roja and Srikant also I see from former NML colleague. Any comments, any suggestion, please go ahead.
And if Professor Mukhopadhyay or Dr. Srivastava want to share my email address, I'll be happy to answer questions if they come up later.
Yeah, sure.
Okay. Maybe not many questions are coming forward. So I think we'll now close it, and maybe from my personal behalf and all the three institutions who organized this lecture series. This time is in NML Jamshedpur. Next time it will be Indian Institute of Science, Bangalore. Then again it will come back to Varanasi. And we would have expected Ken to visit physically, but let's say the short time it was not possible. But in future, you are most welcome to visit all these three institutions and also visit India. That will be very wonderful.
Thank
so
you.
I'm sure people who would like to interact, they can get the email address from Vikas, and they can also later on can contact Professor Ken Kelton for any questions, queries. He's a very good teacher. He explains the things very nicely. I have seen it. So with this, I would like to close it and thank from my side, Professor Ken.
Professor NK, can we have a group? Yeah, can we have a group photograph?
I don't know how to do it. It's a wonderful idea.
Yeah, Professor Kelton, you can just unshare your slides.
Okay.
And people here can click on their video.
Yeah, it will be a good record. I could see Srikant. Srikant, you did not speak anything.
Okay, let's see here. Let me see if I can change so that we all are on.
You are muted.
Let's see. Yeah, I'm trying to get.
Yeah.
I'm trying to get
all
this
it on their video.
Am I okay now?
Yeah, you are okay, but maybe you were muted, so we could not hear you earlier.
Yeah. So it was a very exciting lecture. I have been out of academics for more than 5-6 years now, but it was good to reconnect back with the ideas of nucleation and growth. I just had a couple of curiosities.
Mhm.
One was whether the thermodynamic and kinetic models that Professor Kelton spoke about would also explain why it's difficult to form glasses in pure metals. That's one.
Hmm.
And the second aspect was that with the advent of artificial intelligence and data sciences, could improved models of nucleation evolve, which are based on data sciences.
Mhm. I agree with you on the second one, certainly, that the use of machine learning and artificial intelligence, I think those are going to open up some wonderful information for us. I would hesitate at this point to argue about why pure metals would form a glass. I don't think we need to go into the types of considerations I was making here to argue that. I think it's just simply that the crystallization rates are so high that it's very, very hard to make that. But that would be my thought.
Thank you.
Okay, Srikant.
Good.
Yeah, I think before taking the photo, I would like to tell Ken that Professor Dr. Srikant was one of the main person to start this lecture series,
Mhm.
and his contribution, his really leadership role is phenomenal to start this lecture. And he only was the, so you talked about nucleation. He was the nucleating agent for this
Okay.
lecture. So
Very good.
that's why you should acknowledge
Uh,
him. And another thing, Professor Ramarao, of course, he is not there right now here. And Kamanyu Chattopadhyay, these are the people, they were really played important role. And we hope to continue every year. Normally, we try to do in the month of March, the
Mhm.
birth month, but
Right.
this year somehow it got delayed. But we are really very happy that you could agree to Kamanyu's invitation, and then finally it is materialized, and I'm sure you all have enjoyed lectures. So I would like to thank you all, and I would like to ask Vikas to come forward and take photo, whatever photos possible, and then propose vote of thanks. Thank you, Ken.
Thank you. I've enjoyed it. It's good to see everyone also.
Yeah, thank you, Professor Mukhopadhyay. I have taken the photos of all the people who are available on video.
Okay.
And I would like to thank, on behalf of the organizing committee, I would like to thank and extend our deepest gratitude to Professor Kelton for delivering this Professor Ramachandra Rao lecture and this thought-provoking talk on crystal nucleation and liquid and classes is, I think, is a fitting tribute to Professor P. Ramachandra Rao's legacy in the field of rapid solidification, metallic classes, and these areas. And I'm sure that all the audience, they would have taken this lecture. It would have resonated with them. And I appreciate the time and effort Professor Kelton has devoted for this memorial lecture. And we are really thankful to you, sir, for this talk here online. And I could see that there are many my previous teachers as well as the colleagues of Professor Rao, and Dr. Shrikant is there, Professor Ojha, Dr. M.L. Bhatia, Dr. V. Ramasamy, and Dr. Doherty was here, and Dr. R.K. Mandal is there. So thank you all for joining us today. And I would like to thank Professor P. Ramarao, Professor Kamani Chattopadhyay, Dr. Sandeep Ghosh Chaudhary, Professor N.K. Mukhopadhyay, Dr. Sinha, Dr. Sunil Mohan, Head of Department, Metallurgy Department, BHU, Dr. Satyam Suvas, for their continuous support and guidance in organizing this lecture successfully. And last but not the least, I thank all those who have directly or indirectly helped in successfully organizing this event. And thank you all for joining us today to commemorate Professor Rao's life and work. Thank
Yeah,
you.
that one sentence. It's a special occasion for me that in the memory of my PhD supervisor, the lecture is given by my PhD examiner. So
Oh,
it's
that's
a
great.
Yes, you reminded me of that. I
Yeah.
forgot.
Yeah.
Very good.
Thank you all.
Okay, thank you.
Thanks a lot.
thank you.
Thank you. Thank you.
Thank you, sir. Thank you.
Bye-bye.
And I will
Okay.
stop the recording and we'll talk about how to get it transferred to you.
Yeah, sure.
Okay. Okay. Goodbye. Goodbye.
Bye bye.
Okay.